Hi, everyone. I hope you're enjoying the conference so far. I'm really excited. I hope I won't ruin it. So, I want to talk to you today about bike sharing services. And I think it's a very interesting topic because in Zurich, we've been having more and more of those bike sharing services deployed. And since they were all around the city, I thought it would be cool to have a closer look at them. Who am I? I'm information security passionate. In my free time, I do some hobby penetration testing, as is this project. It's all done in my free time, besides work, besides the family. And it has nothing to do with my current employer, just to let you know. It's not something we do as a business. And in my pastime, I also have bees, and I've been doing that for about 4 or 5 years, and it's a pretty cool hobby, apart from the fact that you get stung from time to time. So the motivation for this side project was actually, so I told you, no, I didn't tell you yet, but I used to work for a penetration testing company, and I did a lot of great projects there. It was super interesting, but there was just one category of projects or technologies I never looked at. There were mobile applications. And so I thought I wanted to look a bit more into mobile apps in my free time, and so break some apps. And so I needed an app to test it, and this is how I came to test the bike sharing services, because obviously you need a mobile app to unlock the bikes. Then, so bike sharing services in Zurich. So you see from last year on, almost 2 years now, we've had bikes that you can rent in the city. There are different modes to rent those bikes. Most of them, 3 of them, the first ones, are free-floating or dockless bike sharing services. This means bikes are deployed all around the city, and you need the app to locate the bike. Then you go to the bike, you lock it, you can ride, and then you can leave the bike anywhere. The one exception is the last one, Publibike, which is actually the newest. So it was deployed a month ago. And this one, you need to get the bike from a station, you ride it, and then you need to put it back to a station. So the first one, Smide, I only had I'm only going to talk about 2 bike sharing services. These are Smide and O-Bike. And we'll look at the specifics of those bikes. But then there's also Limebike, which is a Californian service. And as I said, Publibike, which is Swiss. Okay, so how do bike sharing services work? So you need a smartphone. You need to install an app. You need to sign up, either with a social media account like Facebook or Google, or you can just register with your mobile phone number. You need to buy credits with your credit card, so you load some credits on it, and then you're good to go. You locate the bike on the app. There's a map, and then you can say you want to lease the bike. You start leasing. As long as you're riding, you pay a fee, and then at the end of your journey, you just lock it down. And for all the free-floating services, you can just leave the bike anywhere, which is sometimes kind of a problem, because people usually tend to leave the bikes anywhere, and that's not so good. So, what kind of problems could we expect from an IT security point of view with those bikes? There are first operational issues. So I had it on the title slide. You wouldn't steal a bike. So obviously, if you look at the security system, you'd say, okay, I want to bypass the payment, so you could have free rides. That's one motivation you could have of hacking such an app. Then a second thing you would want to be prepared for is service downtime. So if a hacker is able to shut down the whole system, you won't earn any money. That's bad. Third, operational risk, I would say, is data protection. You have subscribed users, they all log in with their personal information, they have financial information with a credit card. You wouldn't want that data to leak. Then another type of risks you can have are like safety and also liability, because the people renting those bikes will be on the streets, they will be in traffic, and if something happens to them because your bike has a malfunction, then you will be probably liable, and that's not so nice. So all of this has a business impact. I mean, if you know how to hack it to have free rides, then obviously you'll have a financial loss, but also reputational damage. Okay, so let's go on and have a look at the first bike. It's Smide. So it's a company based in Zurich. They were originally backed by an insurance company, and it's pretty interesting because the insurance company wanted to do some research on how people would use new mobility, like e-mobility and like car sharing with vehicles that don't belong to them. And it was kind of like a test bed from there for them to see or to analyze the behavior of people, how they would ride the bike. So the bikes they are renting are also, it's also a Swiss product. It's Stromer bikes, and they're very high quality bikes. They are very nice to ride. They're very powerful bikes, actually, so they're e-bikes. They have a motor in it, and I think, I'm not sure how fast you can ride with the Smide bikes, but if you have one of these Stromer bikes, I guess you can ride them up to 40 kilometers per hour. The unit price is pretty high. If you would want to buy such a bike, it's like 6,500 francs approximately. They have, Smide themselves have a fleet of about 400 bikes, according to what you can see from the API, but I don't know if it's a reliable number, because maybe a lot of bikes are in maintenance or not deployed at the moment. And how are the bikes tracked? They have an integrated GPS module, and they communicate with the backend with a GSM modem. So you can do fleet management with them. So let's look a bit closer at that, how that works. So, as I already mentioned, the bike communicates with the GPS satellite, so it knows where it is. It also has a GSM link to the base station and talks directly to the Smide backend, which does the whole fleet management. On the other side, you have a mobile app, which also connects to the backend, which manages all bookings, or if you want to lock the bike, if you want to unlock it, and so on. So the bikes are autonomous, and if you were to steal them, then you have some protections against that. Let me see. Yeah, we'll see about the protections afterwards. So let us have a look at the API on the mobile side, because I analyzed the mobile application. So this is the call you're using to get all the bikes. You just do a REST call, and then you get a JSON response of that type. So obviously you have a lot of more of that records. You get an ID number, you get the number plate of the bikes, you get its battery level, you get the approximate address where it is, and the GPS coordinates. So theft protection. If somebody were to take the bike and move it away, then this is a feature of Stromer, that the movement would be detected, the fleet management would get an alarm, and the Smide people would start and try to figure out where it is. So There's another feature is like when you lock down the bike, you don't have a physical lock on it, but you have the motor has an electronic lock. That means the rear wheel is actually blocked and you can't ride with the bike. And as soon as you unlock the bike, then you're free to ride it. Let's look at the booking process. It's pretty simple. So you find a bike on the left side, it's vacant and it's locked. Then you start the booking, you unlock the bike, and then while you're riding the bike, maybe you want to lock it, but keep the booking, because maybe you want to do your groceries, but you want to get back on the bike afterwards. So you have the ability to keep the booking, but lock the bike, and then you come back to the bike, unlock it, and ride again. So let's look at how this is done. First of all, you need to authenticate. Authentication is pretty simple. You give in your email address, your password. So you have different login types if you're using, how do you call it, social media or not. I'm using here my own email address. And then you get a JSON Web Token as an answer. So if you don't know how a JSON Web Token looks like, it looks like that. It's a series, it's a block subdivided into 3 parts of base 64 encoded stuff. So let me show it how it looks like. So you have a header, which tells me it's a JSON Web Token, and you're using HMAC SHA 512 to sign the assertion. You have a user ID, you have a timestamp, and an expiration. And this is kind of like a signed token that you can pass on for all the subsequent calls that identifies the user. Okay, so now we have JWT token, JWT, and we want to unlock we want to initiate a booking. So what you do, you post on the REST API booking, and you put in the HTTP header, you put in this token, this auth token. You say which bike you want to book, number 133, and you also give in your user ID, which is redundant because it's already in the token. What you get as response, you get a booking ID as a response. This is the booking ID you're going to use for every operation during your ride. You have an active flag that says you're currently using your bike right now, so it's unlocked. No, it's not active, it's a usage flag actually. So now it's in false. You have a second call where you can then unlock the bike, and then the usage flag will be set to true. And you have some timestamps. Okay, so let's assume I'm riding the bike now, and I want to stop at the grocery store, and I want to lock the bike but keep the booking. What I'm going to do is I'm going to call another REST API, so on the booking 12345 usage, and then I'm going to set the usage to false, and thereby telling the backend that I want to lock the bike. And the backend tells me, okay, usage is set to false, and you have a PIN code. If you weren't able to unlock the bike with your mobile app, you could still use the PIN code and enter it on the display of the bike. Okay, so I thought, what if I have a second user that uses the same booking ID? And what I also noticed is that the booking IDs are sequential. So actually, you could, if I have a booking ID 12346, I could go in the past 12345 and get the booking ID of another user on the street, and then tell him I want to lock the bike. And what happens is it works. So that's a kind of risk that goes into safety and health issues. When I found this out, I reported it to SMIDE. They didn't have a security contact, so I just used their info contact. I did the report late in the night, but and this was a Saturday. So on the same day, in the afternoon of that Saturday, I got a confirmation of the supporter, and he was like, okay, thanks a lot, we'll have to look into it. And then 4 days later, I got a confirmation from the product owner who told me, okay, well, thanks a lot for the report. They already had fixed it on Monday, and I could test it, it was fixed, so it was really cool. They offered me 100 minutes for free ride, and yeah. But I really enjoyed the communication. They took it seriously, they responded very fast, and as you will see, it was not always the case. Okay, so that was all for Smide. Now let's go over to O-Bike. O-Bike is another kind of service. It's also free-floating. It's not from Switzerland, it's from Singapore. It's deployed in a lot of different countries. And actually, it's some cities are starting to ban O-bikes. So Munich and Melbourne in Australia are banning O-bikes because everybody leaves them around or puts them in the river, and they think it's an environmental issue. The bikes are different than Smide in that they're super cheap. They're not, well, the estimated cost is maybe $200, including deployment to the countries. They have only a single speed, so no, it's not an e-bike. You have to ride it yourself. It's totally maintenance-free. They have solid rubber tires, so nobody needs to go and maintain the bikes. I mean, with the e-bikes, you always need to go after the bikes and replace the batteries because eventually they'll be empty. And if you look at the fare, it's also a cost model that's way cheaper. Okay, so let's look at the interfaces. It's also much more simpler. The bike itself is not autonomous. It only has a Bluetooth low energy link to the mobile app. And actually, everything, more or less everything, is done on the mobile app. This means location tracking is the mobile app, and communication with the backend is done through the mobile app. So actually, the mobile app is kind of like man in the middle. So let's see how the REST interface looks like. If you want to have a list of all the bikes, same as for Smide, you just you just say which point you want to have the bikes, then you get all bikes in a radius of, I think, about 1 kilometer. So you get a whole list of them, you get an ID, you get the coordinates, and so on. So actually you can map all the bikes. So, but as you can see, I mean, it's the mobile application who's telling the backend where the bike is located at the moment when you're locking or unlocking the bike. So how does it look like? You put the location for a certain bike, so you have the bike ID and the new coordinates, and the backend tells you something in Chinese. Well, location report success. That means that actually, if we come back to this one, if somebody was funny enough to put, well, he could like put all the bikes in the river, and everybody would see on their mobile app, couldn't find any other bikes, so you could spoof the location of all the bikes. Or if you want, I mean, you could do like ASCII art with the dots. I'm hearing challenge accepted somewhere. Okay, let us look at the hardware. So I found those pictures on the website of FCC, the Federal Communications Commission of the USA. And it's pretty cool, so to see how it's built up. So this is the lock, how it looks like when it's opened. And what you see in the blue part in the middle, well, everything is blue, okay, but there's a pretty large battery inside it, but you also have a solar panel, so the solar panel recharges the battery. Yeah, here we can see the battery a bit better. And then you have, well, two PCBs. One of them has a little beeper and a knob, a button, push button, and the other one has the whole, chips on it. What you also see in the middle is a latch or lever, which will actually unlock the bike once it's, so you have a little electrical motor, it will just open the latch, and then the whole lock will fall down because of the spring. Well, no, well, it goes up, yeah, well. There's a quite neat video, I think, from an Australian guy who took a whole lock apart, and it's just one screenshot because on this image you can see quite well. You see the imprint of the chip, which I couldn't see on the FCC images. So it's the system on a chip that's used. The main chip on the PCB is a Texas Instrument ChipCon 2541, which is a system on a chip specialized for Bluetooth low energy communication. If you look at the specification of the chip, you see that it has an AES processor, which says, okay, can do crypto. And these are the different modes the processor can support. So you see it can do AES 128, and it has support for ECB, CBC, CFB, OFB, CTR modes, but also CBC MAC, which I assume is used for the crypto in the protocol. CBC MAC, I'd say, is kind of like a digital signature, but using a symmetric key. So if anyone knows the key, he can sign the messages. Okay, so I had a look at the Bluetooth communication, so between the lock and the mobile phone, and try to reverse engineer it to see how it works. This is the overall comment structure. You always have a preamble that's fixed, it's always the same. Then you have a length for the payload, you have a command type, you have then the payload, and then a check byte. What's interesting in the command type is you can figure out the direction of the command. So if the third bit, the third bit in the first nibble, well, you have 0x8, it's going to be a communication or a message from the mobile to the O-bike. And if the bit is set right besides it, so you have 0x4, it's going to be in the other way. Also, if you're interested to know how the check byte is computed, it's just by XORing the individual bytes of the payload and the command type. Okay, so let's have a look at the first message sent from the mobile phone to the lock to initiate the communication. It's an empty message. You see length is 0, there's no payload, and obviously the check byte is the same as the command because it's the only byte which is used in the checksum computation. Then you get a response from the lock, which just has the byte set as a response, but it's also an empty response. Okay, so the next message the mobile phone will send to the O-bike is actually, here are your coordinates. And the chip will store the coordinates, so it has some persistence, so it knows maybe for later on where the bike was located. So as you see, what's interesting here is that they use 1 byte less for the latitude, longitude. Well, yeah. But there are a lot of strange things going on. But I mean, it's the precision is high enough, so it's okay. What you get back from the lock is you have some constants. I couldn't make any sense out of them, but the interesting part is this 32-bit challenge, which is a random number which will be sent to the mobile phone, and the mobile phone will send this via the REST API to the backend. And they call that, in the REST API, the parameter is called key source. Afterwards, you get a response back from the backend via REST API, and actually it's kind of like a response to that challenge. And you also have a key index. So the response looks like, I think it's the CBC MAC, but it's not 128 bits, it's only 96 bits, and I don't know why. They just truncated it, but I mean, it should be still enough bits if the chip does the same computation on its part to compare it. But still, there's some room for randomness there. And what's also interesting is that you always get a different key ID, and I think from what I've observed, there are maybe about 100 different key IDs. And I think it's the key that is shared between the lock and the backend, and they just tell you, okay, I calculated the MAC with this key, with this specific key. Okay, at that point, the lock opens, and the lock generates also an acknowledge message, which is also signed. And you have all sort of information. You have timestamps, well, actually twice, once big endian, once little endian. You have a bike ID, which is actually a part of the MAC address of the Bluetooth interface. Then you have the stored coordinates, and then this message has a CBC MAC of 128 bits with another key ID, which will then be validated by the backend. Okay, so I guess you can already figure out the whole security relies upon those shared keys, which are actually on the chip and also on within the backend. So what's interesting is this is another picture from that I taken from FCC. You see, so the chipcom chip, and above you have like 5 pads, which I guess are debug pads. So I asked Obike, I requested, I did a request if they would be willing to give me a test lock because I want to look into it, obviously, with the debugger, and to see if I could extract some of the keys. But I got no response. So time went by, and I was like, I mean, I was not working always on the project, but I was still regularly Googling stuff about Obikes every time Obike would come in the news. And I found an interesting PDF from, it's a student project from the new University of Singapore, where I figured out, well, they were also looking into the Obikes. And they had another focus. They also looked at the REST interface. They looked at a lot of different aspects. They didn't, in the paper, they didn't invest so much time as I did in the details of the Bluetooth communication. And actually, it dawned to me, I was too deep in the details, and they had a wonderful description of vulnerability, which I can show you in the next slide. So if you paid attention, maybe you already found the problem. So this is high-level description of the protocol. So the Obike sends the challenge to the mobile app sends it to the backend. The backend responds with CBC MAC, which the Obike validates. At that moment, the lock opens. What you do from now on, the lock computes an acknowledgement, and only at the time where the backend receives the acknowledgement, it starts billing. So fail number 2. Okay, so obviously that way of doing, you would have communication with the backend, so they can detect what's going on. What happens is, if the backend doesn't receive the acknowledgement, there's some logic on the backend that tells you, okay, this byte must be broken because it haven't sent me, it initiated the unlocking process, but it didn't finish it. So they flag the bike as being broken for 24 hours. And if you think about that, that's another fail, because you could do that with a whole range of bikes, and you're DOSing the whole system. So every bike is not available for a period of 24 hours. Okay, so after some time, in fall of 2017, I realized they changed the REST API. So as usual, I wanted to get the list of bikes, and then I got an error. Serve is busy, please try later. Not very useful error. And I noticed there was an update of the app, so I looked into the communication again, and then the call had changed. Actually, it was like a hex payload, but I couldn't make any sense of it until I realized, okay, it must be something encrypted. And in the news, you could see, okay, somebody else found a way to leak all data of all users of O-Bike, so you could access the personal information, mobile phone numbers, but no credit card numbers. And I think it was as a measure or a reaction to this leak that they changed the API and made it more secure. I don't know. So I thought, well, if the mobile app knows how to encrypt those messages, so the key must be somewhere in the app. So I used tools to decompile the DEX files, Java files, and couldn't find anything there until I realized, okay, they hid the keys inside a native library. And so, as you can see here, it's for the x86 version. You also have the ARM version and so on. And in every of those shared libraries, you would find somewhere, if you dump the library, you would find the needed keys to do that. And how is it used? So first of all, it's not only encryption, it's also integrity protected. So first you have an integrity protection with a SHA-1 hash, and there you need the first key, this OBADDX, and this was used under Android. And I figured out other people are also find that out because they wanted to develop a global app to find bikes of different sharing services. So what they did is they also reverse engineered it, but they use an iOS phone. And I figured out this ADD means Android. In the iOS version, you would have an iOS at that place. So you need the plain text, which is just a JSON payload, and you have this ampersand. You calculate the message authentication code by concatenating all this stuff and computing the SHA-1 out of it. Then afterwards, you're going to use that MAC again using the plain text, the ampersand, and then appending the MAC. You put it into AES 128 CBC with an initialization vector that's very random. This is 1, 2, 3, 4, 5. And then the other key, plus the app version number. So I used the app number, the version number 2.5.4, and you had to take the individual digits, so like 254, and just append it to this key. And then you would get the ciphertext. So if we look at the payload I had just before, when you decrypt it, you get like this. And what's interesting is that now they're also tracking the device ID when you want to access the bike locations. So it's more of a security by obscurity strategy, and I don't know what they wanted to reach with that. Okay, so I'm already at the end. I have some conclusions. First of all, think about the risks when you're developing such a system, because there could be obvious and less obvious risks. I'd say the safety issues are less obvious, and you need to think about them. And another point, I don't want to lobby for the penetration testing companies, but I think it makes sense, especially when you're deploying on such a mass scale. I think you could invest maybe $10,000 or $20,000 to do a basic security audit. But because actually I'm doing this in my spare time, and I think I got a lot of low-hanging fruits. So you could get rid of those low-hanging fruits by just having some security guys looking at it. Then the third thing I want to say is, eventually there will be design flaws, as we saw, or the keys will be leaked. So you need to prepare for that. You need to make your devices fixable. So in the case of O-bikes, I guess it's not possible to update the locks over the air. Well, I didn't find anything in the app that would go in this direction. Of course, maybe it's possible, but because you would want to avoid to go out to all the bikes and reprogram the stuff, that would be almost infeasible. So you need to keep that in mind and have some mechanism to allow to update the code on your devices. Okay, so before I go over to the questions, some comments, because I see I have some time left. If you want to see all the description of the reverse engineering, so on, I just put it on my GitHub account, so it's Antoine T/obike. If you want to follow me on Twitter, it's Antoine T, but with a 0 instead of a O. And a third reference, there's a Twitter account called Broken O-Bikes. It's super entertaining. So it's someone who's gathering pictures of O-bikes in all kinds of funny situations, like in the river, on trees, stacked on another, or like people who are changing the aspect of the O-bike. Just look at it. It's really pretty funny. Then I have something else I discovered during the analysis is if you paid attention during when I showed how you could get the location, you have one field, it's called IMEI. And at first I thought, I didn't know what's inside the lock, so I thought, okay, that's clear, that's the International Mobile Equipment Identity, that's something that would identify the GSM module. Like every GSM phone has an IMEI, and it's used to track the phone, actually. So I thought, okay, it must have some means of communication, but it's not the case. So it's probably another acronym. So I looked at, and it's not at all the format of an IMEI, but it's a hex string. So I looked at the hex string and saw it's all in the ASCII range. And actually, some of the values, you can overlap them, and you see it means something. So it's very interesting. So this is just an excerpt of what you see. So it says initialization function, simple BLE peripheral. And so for me, BLE is like, that's Bluetooth Low Energy. So that's kind of like function names that are used on the client, but I never needed those actually to make the whole thing work. So I have no idea what it is. Maybe it's a memory leak. So if somebody ever finds out, I'd be interested in knowing. Okay. So thanks a lot for your attention. And
okay, are there any questions?
Thanks for the interesting talk. How did you test this stuff? Brought you the bikes to your home?
Well, you can see it on this photograph. This is somewhere in Zurich. I just brought my computer to the bike. Sometimes I even put the bike somewhere closer to where I work, so I can access it. But they have a range of about 10 meters, so with the BLE, so you don't really need it to have it just close to you. Maybe if you have it outside the window, it's already enough.
Another question?
Did you disclose to O-Bikes that you were able to extract the AES keys? And if so, how did they react, if at all?
I didn't understand the part with the AES keys.
Did you disclose to O-Bikes if you you extracted the AES key, how they?
I didn't extract the AES keys. It's just it was not a dead end, but actually since I didn't get access to a lock, I didn't go further that way. I tried to contact O-Bike at several occasions, either through their support, which I think is in Singapore, and otherwise via the contacts in Switzerland. And I mentioned the paper of the new University of Singapore, which was publicly accessible on the internet. And the response was very fast. They told me they fixed the problem. So afterwards, I informed them that I would mention this bug in the security conference. And then I didn't have any response anymore.
Any other questions? Okay, doesn't look like that. So let's thank the speaker again.
Thanks.